In the previous class, we considered the sinusoidal steady state behavior of circuits, but that analysis was focused more on getting the so called frequency response of the circuit, which is in fact the sinusoidal steady state response at various frequencies in terms of the magnitude scaling as well as the phase shifts which are caused by the circuit. The underlying theme of course was, or rather the important point which was mentioned was that for certain kinds of signals, typically DC signals or e raised to st kind of signals, which are applied to linear circuits, that is circuits with inductances and capacitances, resistance whose values are not dependent on the current, but are constant. Such linear circuits, if you apply sinusoids, exponentially decaying inputs or DC inputs, the wave shape does not change, that is in steady state of course. So, of course, before you reach steady state there is a transient, but when you reach the steady state, the wave shape of the measured output and the input is in fact the same. Of course, one should I should further qualify the statement. When I say the wave shape does not change, what I mean is if your input is of a particular, say it is a DC, then the final steady state is also a DC. If you give a input sinusoid of a particular frequency, then the output is also the same frequency sinusoid, but with a phase shift and a scaling, that is a magnitude change. But of course, I should again make it very clear, if you give 2 or 3 if your input signal is consisting of 2 or 3 sinusoids, your output also has got those sinusoids at those frequencies, but in fact for every each sinusoid, there are different phase shifts and magnitudes depending on what you connect. Especially if you have got RLC type circuits, there are invariably some phase shifts and scalings which occur, which are different for different frequencies. So, when I said wave shape is preserved, I mean the case when you have got an input which has got one frequency. If you have got inputs with several frequencies, your output is a superposition of the response for each of those frequencies, but since the phase shifts and magnitude scaling is different for different frequencies, the wave shape in this case, the composite wave shape, when you consider all the inputs and all the components of the input and all the components of the output, the output wave shape may actually look different from the input wave shape, although it contains exactly those frequencies which are present in the input. So, in fact, because of this most circuits will distort inputs in which there are several frequency components. Just to make this more clear, let us just look at this simple analysis. So, let me just make it amply clear. If you have got e raised to st plus alpha as an input given, let us say it is a voltage input given to a linear circuit, and you measure the voltages and currents at some point in the circuit, in that case the output is also some b e raised to st plus alpha into e raised to some other phi. I mean, of course, this you can have complex numbers. For example, when you have got sinusoids, in fact you have got, suppose you have got e raised to j plus alpha, then you can have the output to be e raised to j omega t plus alpha and also a phase shift. For example, a phase shift of minus phi. So, this a gets scaled and there is a phase shift. If of course, the wave shapes are the same. So, that is an important thing. But in case you have got 2 or 3, for example, you have got sin omega t 1 t plus sin omega 2 t as your inputs a 1 and this is a 2 and this is alpha 1 and alpha 2. This of course can be expressed again as a sum of exponents with complex exponents e raised to some complex exponent. So, if you in fact have circuits of this inputs of this kind, the output is b1 sin omega 1 t plus alpha plus phi or minus phi and b2 So actually you will see that the wave shape of each individual component is preserved, but actually when you see the wave shape of this composite term, it may not be preserved. For example, you can give a square wave to a RL circuit as a voltage input, and the current may actually look different. In fact, the current depending on this RL value will look different. For example, let us just take a 50 hertz square wave. So, this is roughly this is 20 milliseconds, and let us say you feed it to an RL circuit which has got a time constant of that is L by R is equal to let R be 1 ohm and L be such that L by R is say 0.001 milliseconds, 0.11 second, that is 1 millisecond. Then what you will find is your final steady state. I am not talking about the transient. In steady state, your output may look like this. So, the wave shape has indeed changed. But the interesting thing is that if you look at all the individual components, whatever frequencies are there, if you split this using the Fourier series into its individual frequency components, you will find that all those components are present here. But since the scaling and phase shifts are different for each of them, the wave shape changes. Now, what implication does it have? So, the thing is that whenever you are talking of electrical power supply systems, it's easier to design the equipment or utilize equipment and design equipment when you know the wave shape in advance. For example, if you know that a certain component is going to be subjected to so and so DC voltage, then you can design it accordingly depending on how much current is likely to flow, how much heat will get dissipated and so on. If you know that the voltage which is going to be or the current passing through an element is sinusoid, then too you can actually design it for a sinusoidal wave shape. You know roughly how much the average the root mean square of that sinusoid will be and so on. But suppose I try to have a supply system in which the input is a square wave. Now, the interesting point is that if I apply a square wave say to an RL circuit or a circuit containing RLCs, the final steady state waveforms are in fact not going to be of the same wave shape, because each individual component gets scaled and phase shifted separately, differently, and therefore, the wave shapes are different, and in fact, the shape of the wave again depends on the nature of the component. So, I cannot really design the component knowing the wave shape in advance. So, suppose I am sending a certain square wave over a certain distance using a transmission line and transformer and so on. What I will get at the end of that transmission system or the point at which the load is going to be connected depends on the transmission system, because if I change the LCs of the transmission line, of course, we have not modeled the transmission line in detail, but I can show you later that we have got L's and C's of a transmission line. The transformer also has got what is known as a leakage inductance, and of course, we got a feel of that before when we talked about mutually coupled circuits, and even in transmission lines we discuss in passing things like parasitic inductances and capacitances. The transmission line in fact has these distributed or we can call them parasitic, but they are much more dominant than just being parasitics. Now, so what happens is that if you give an input to such a system which is not of one frequency, then we cannot be tell what the kind of wave shape will appear at the other end. So, then that becomes difficult to design such a system. It is not that you cannot design a system say for a square wave input, possibly you can, but the point is that when you design a transmission and distribution system of electrical supply, you should be kind of sure what kind of wave shape you will get at the end. If you have got an input with one frequency, then you can be sure that you are going to get the output also of that frequency if you have got linear circuits. In fact, most transmission and distribution systems are designed to be linear, at least in normal operating region. So, normally we in a power system usually work with DC or with sinusoid of one frequency. If you use sinusoids of many frequencies, you will see those components in the final waveform, but since the magnitudes and phase shifts are different for different frequencies, you will see that the wave shape has got distorted. So, if you give a single frequency input, the wave shape is preserved. So, that is the important thing. Now, we just do a quick review. This is a relatively straightforward lecture in which we just review what probably you know already. So, let us just take a simple system. What we will do is look at the analysis of a simple circuits. In this case, it is simply an RLC circuit using in the time domain and in what we call as the phasor domain. Now, when we are talking of phasor domain, this is essentially replacing the L's by j omega L or SL, but with S is equal to j omega. I have in a previous lecture shown you that you can in fact just by plugging in S is equal to j omega get the responses, infer the phase shifts and magnitudes when you actually apply inputs like e raised to j omega t or even sin omega t or cos omega t. So, one of the ways of representing these inputs, since we know that a single frequency input will actually give output in sinusoidal steady state of only that frequency, we can in fact represent the input and output simply as phasors, because we know that they already have a component which is sinusoidally varying. Only what we can capture is the phase and magnitude information. So, when I for example represent Vs is equal to 100 sin omega t, this is a 50 hertz waveform, then one of the ways of referring to this sinusoid, once it is implicit that this is containing that frequency, is Vs is equal to 100 angle 0. Okay. So, what does it mean? This has got a magnitude of 100 and the phase angle, if you assume sin omega t is a reference, then this has a phase shift, the source has a phase shift of angle 0. So, what this means, this is effectively a phasor. It is implicit that it is varying at 50 hertz. Okay. This is varying at the frequency, and although the frequency is not given, it is implicit that there is a normal frequency you are referring to. Now, an important thing when you represent sine waves, remember that the source I have not only depicted by a circle with a a kind of a sine wave in it in the figure there, if you look at the figure there, yes. So, you see this, yeah, but of course, I have also given plus or minus sign. This is just to show that Vs is the potential difference, that is the potential of the top point with respect to the bottom point. Okay. So, that plus minus means that. So, this is the voltage which is there, this is the voltage rise you can say when you go from bottom to top, and this is 100 sin omega t and is represented as a phasor. Okay. So, of course, once to get the kind of finally, of course, what we need to do is solve this circuit. So, a simple way of applying Kirchhoff voltage law, we have done this before in a sense, because we have tried to look at it more generally for e raised to st plus alpha, but you can of course get the use the same analysis for e raised to j omega t for DC inputs with s is equal to 0, or you can also get sines and cosines, because sines and cosines are in fact e raised to j omega t, combinations of e raised to j omega t and minus j omega t. Okay. So, now this seems to work quite well, that is if you apply KVL you can do this analysis with phasors. Since it is a phasor, I have actually put a bar on the top, there is no standard notation for this. Another way of one more notation we can have is use capital letters or uppercase letters for phasors and lowercase letters for instantaneous quantities. For example, Vs of t is a instantaneous quantity. So, these are all conventions, they are not standard, but I think more or less we will kind of try to be consistent with these conventions. I have added a bar also on top of it. Now, when you divide it by r plus s, s is of course you can replace it by j omega L as I said and j omega c, and this bottom term in fact is a complex number. So, you can actually get the magnitude and phase shift. So, for example, the phase shift caused by r is r plus j omega L plus 1 upon j omega c. You can quickly evaluate it and see tan inverse omega L minus 1 by omega c divided by R is going to be in fact is going to be minus 58.2, and therefore, the current in fact will be 58.2 degrees leading the voltage. So, this is what we actually get. So, 5.27. So, actually once you get this phasor, it is easy to interpret what actually you are going to get in the instantaneous domain. So, the sinusoidal steady state solution is in fact got by this. Okay. As I mentioned in the previous lecture, the interesting fact about this whole analysis is that the denominator term which you see here, if you take the roots of it, that is you find out, you just replace j omega by s and try to get the roots of this equation. They also tell you how the natural response will look like, and remember, the natural response frequencies or the real parts of the roots of the equation need not have need not be correlated that easily with this phase shift at a particular frequency, that is at 50 hertz. Okay. Yeah. Of course, one interesting thing is that in series RLC circuits, if you choose omega equal to omega L is equal to 1 upon omega C, you get what is known as the resonant condition, in which this current is maximum. Okay. So, you will have a very large current in case if R is small, then there will be a large current in case omega L becomes equal to 1 upon omega C. That is the resonant condition, or the frequency at which resonance occurs. In this circuit, in fact, omega, which is 50 hertz, is not at the resonant frequency. So, we are not going to get a resonant condition. But interestingly, omega L is equal to 1 upon omega C is also the imaginary component of the root of the characteristic equation which I was talking of. So, there is an interesting relationship between the natural transients and the kind of calculations we do for phasor computations. But remember that what I have shown you at the bottom left is the expression for the sinusoidal steady state current, which of course has no mention here of the natural transient. Yeah. Of course, the same circuit, some people like to use cosine signals as references, in which case of course V of t, which is same as before, is represented since sin omega t lags cos omega t by 90 degrees, you can represent Vs as a phasor 100 minus 90 degrees. So if you take cosine as reference, the same analysis can be done, and finally of course the current phasor also looks different in the cosine domain, and finally of course you get the same answer. So the same answer you get of course as before. So if you are in the phasor domain, as long as you know whether you are using the cosine or the sine as the reference, you can finally get a time domain solution. This is an interesting thing which is related to measurement in power systems or electrical supply systems. Normally electrical power systems, especially bulk power systems, can be spread over huge geographical areas, even a continent. You can have an interconnected system over a continent, and suppose you have got measurements taken at different points. Say you are measuring the voltage at current at some point, and you are measuring it, it is a sinusoid, because all our AC systems are in fact single frequency sinusoids. You find that if you want to connect, kind of compare these measurements taken at very far away locations, you end up with one small problem. For example, I could measure all the samples of the voltage at a given place and say Mumbai, and then again at the same time roughly you are going to do the measurements in Delhi, and I want to take out the phase angle difference between voltages measured in Mumbai at say the plug point here and a plug point in Delhi, and I want to compare them. Now one interesting problem arises here is, if you are doing this measurement, because the clocks here and at Delhi may not be synchronized, I may not be able to tell you very easily what is the phase relationship between the voltages measured here and in Delhi, unless we have got synchronized clocks. So I should take the same reference, for example, if I take a sine reference with time t is equal to 0 defined say at 5:25 on 23rd October as my time reference. as my time 0 and take sinusoids as the reference waveform, the same reference should be taken by the person in Delhi. But as you know, the clocks of different places, it is not easy to synchronize. In fact, you could easily be several seconds away from each other if you consider our normal clocks. So you need a very high level of synchronization in case you want to actually answer the question that at this instant the voltage, sinusoidal voltage is appearing at the plug point in IIT Mumbai. IIT Bombay are a certain the phase angle is 20 degrees, say, with respect to this time reference. What with respect to the same time reference is the phase angle at this instant in Delhi? So that is a difficult question to answer unless you have got synchronized clocks. But it turns out that there is a technology now using GPS satellites, which are there in these are constellation of satellites, because of which you can actually have very precisely synchronized clocks. Synchronization accuracy several maybe of the order of microseconds. In such a case, for a 50 hertz wave, without much error, you should be able to, if two clocks are synchronized to each other, that is my clock which shows 5:26 here right down to the millisecond, I give the timing, and the other clock also you get the timing right down to the millisecond, you will find that the two clocks are synchronized to each other. And that kind of synchronization is in fact possible with GPS technology today. And it is possible to measure such voltages, phasors at different locations in an electrical grid now, although the grid itself may be spread over a huge geographical area. So this is about using a common reference. So in the entire circuit here, which is shown here, this is a very small circuit localized using lumped elements, but you can have circuits which are spread over geographical areas, and in that case you should have a common timing reference and also a common whether you are taking cosine as cos omega t as your angle 0 or sin omega t as angle 0, there should be absolute what you call clarity as far as that is concerned. Yeah. Of course, one more interesting point, I use in fact the peak value of the voltage as my reference. In fact, if it is 100 sin omega t, in some books they use the convention that when you write the phasor, you use the RMS value, the root mean square value. So root mean square value for a single frequency sinusoid is simply 1 by root 2 times the peak value of the sinusoid. So why is this root 2 factor where is this root 2 factor coming from? We will come to that a bit later when we consider the power in a sinusoidal circuit. So if you got a single frequency sinusoidal input and you are trying to compute the sinusoidal steady state solution, what you will find is in fact that some books use the RMS value when they define a phasor. So for example, here the phasor is defined as 70.71 angle 0, and when the answer comes, of course, when you apply this phasor analysis, the current is also going to be in RMS, and because it is in RMS, when you actually try to take out the time domain waveforms, you should convert that RMS value to the peak value when you apply that amplitude value to the sine wave. So finally, the answer is of course the same in the time domain. This is only a matter of convention. Okay, so but you should be aware of that. Yes, and of course this is trivial. You can do the same with cosine as a reference. Yes. So one of the interesting points, a quick look at this circuit which is fed from a voltage source. If you want to get the current through it, you can do phasor analysis, and one of the ways to do phasor analysis is in fact get the impedance transfer function, which is a function of the frequency as we did earlier. In the earlier case it is R plus j omega L plus 1 upon j omega C, but of course you can have more complicated circuits with capacitors, inductors, even later, which is the mutually coupled circuits, transformers, and things could be pretty complicated. So this is the driving point impedance function if you want to get the current at the source. This is of course, you can of course generalize this. If you have got 2 port networks, you can in fact have impedance matrix. For example, a 2 port network will have 4 terms, 2 driving point terms at the two terminals and also the off diagonal term. So, you have got an impedance matrix connecting two voltages and two currents if you have got a two port network. But for this simple circuit, of course, you have got a single port network, and this is simply a summary of what we have done so far. In this the Z is assumed to be having an angle which is given by the angle of Z equivalent. So, Z equivalent is a complex number. Okay. So, what you have here is phi, which is in fact the angle of Z. So, what you are showing here is phi is the angle of Z, and mod of Z equivalent is of course the magnitude of Z equivalent. Of course, we move on to another quite a a straightforward topic in a way, but an important one nonetheless when we talk of power supply systems. This is regarding the instantaneous power in a single phase circuit. So, single phase, I mean you have got one single frequency sinusoid of just one single frequency sinusoid as an input, and you suppose have a current which is given by this expression Im is the maximum value of the sinusoid into sin omega. It is lagging, say, the voltage. Okay. So, I have chosen my time reference such that the voltage is V sin omega t and Im lags it by it turns out that it is connected to a circuit which makes the current lag the voltage in sinusoidal steady state. Then the instantaneous power is actually given by simply the product Vi. Okay. So, product is power is essentially the voltage into the current. Why this is so is something you can think over. So, when you actually take the product of V into I, which is the instantaneous power in the circuit, then what you see is what you will get is this expression sin omega t and a bit of trigonometry here, the product of two sinusoids sin A sin B you can say, and you must be aware that if you actually expand this, what you will get is half of Vm Im, because sin A sin B is in fact you will find sin A sin B is given by 1/2 cos A minus B minus cos A plus B. So, you must be recalling, you may recall this formula of basic trigonometry, and from that you get this expression. So, what you can see is that there is one expression which in fact is multiplied by cos phi and the other one is multiplied by sin phi, and the first expression has got is always positive, well, I am not talking of the first expression, rather I should say cos phi into 1 this term 1 minus cos 2 omega t is in fact always greater than 0, whereas if you look at this term it is in fact has got a 0 average. Okay. And an interesting thing is the electrical power P of t is actually varying, it is not constant. So, in a single phase circuit the power is not constant, it is varying at twice the frequency of the input. So, that is an important thing which you should remember. Yes. If you actually, since the power is varying, it is important to have a notion of average power. So, if you got for example a single phase circuit and you want to find out the average power, because P of t is not a constant, it is varying at twice the frequency. So, actually if you take the average of P of t over a cycle, you will find that that is then you have to actually integrate this expression over a cycle, and if you integrate this expression over a cycle, that is when I say cycle I mean the period which is essentially omega by 2 pi, the reciprocal of omega by 2 pi or 2 pi by omega is the period. So, if you in fact try to integrate this over a period of the wave, you will find that as long as you evaluate this integral over one period irrespective of when you start it. So, in case for example, so if you look at this first term cos phi Vm Im cos phi, I will just take the first term here cos 2 omega t, you integrate this over a period. So, you can take any period. So, this is a integration over a period and you take the average value of it. So, this is the integration over a period, this t is equal to 2 pi divided by omega. So, if you do that, you will find that this comes out to be Vm Im. I will not work this out, it is quite trivial. What we see here is in fact half of Vm Im cos phi. In fact, half of Vm Im cos phi can be written as Vm by root 2 into Im by root 2 into cos phi, and Vm by root 2 is in fact the RMS value. So, that explains why we use the RMS notation a few slides ago. Some people would like to use RMS notation. If you use RMS notation, this half need not be used here. You can directly use the RMS value, product of the RMS value. In actually, the second term here which you have sin omega t, sin 2 omega t, the coefficient of that you used along with Vm Im by 2 is also called the reactive power. So, this reactive power, remember, is it is defined in this fashion. So, if you split the expression into the components corresponding to cos phi and gather all the components corresponding to sin phi, then in fact the reactive power comes out to be half Vm Im sin phi. This is a definition. Real power has got real physical meaning in the sense, or a much easily understood physical meaning. It is in fact the average power. Real power is also called the average power or active power. This is in fact the one cycle average of the instantaneous power. Reactive power is, mathematically speaking, one component of the oscillating component of the instantaneous power. So, it is one, there are two oscillating components, cos 2 omega t and sin 2 omega t. So, one of these components here we in fact use for defining reactive power. Is that okay? So, this is essentially half of Vm Im cos sin phi. So, this is a definition. Let us try to understand what this reactive power means, or what is the significance of this term, because remember, average power is something we can understand, whereas reactive power is by definition the coefficient of one of the components of the instantaneous power expression. So, what does it mean? I mean, okay, it is one component, but what meaning can we assign to it? Right now we can take it just like a definition, but let us try to assign some meaning to it as well. So, if you for example take assuming that the current does not lead the current is exactly in phase with the voltage, then phi is equal to 0. So, if you go back to the earlier expression, yeah. So, your current is in fact if you look at the current will be in phase with the voltage, and if that is so, the instantaneous power which is shown in red here is in fact always positive, and because it is because phi is equal to 0, the sin phi component of it is 0. So, that is an interesting point which you will notice. In fact, phi is equal to 0 means there is no phase shift between voltage and current. This happens in fact if your circuit is completely resistive. So, if phi is equal to 0 means the current and voltage are in fact the sinusoidal voltages and currents are in fact exactly in phase, and that happens only if you got a resistive circuit, or equivalently you see a circuit and at that frequency it appears to be a resistive circuit, purely resistive circuit, then this happens. So, this is the case when phi is equal to 0. An interesting thing happens when phi is not 0. For example, if you take phi is equal to 45, the instantaneous power, we have very conveniently taken Vm and Im to be equal to 1 here. The peak value of the instantaneous power of course comes out to be Vm Im as as pointed out. So, there is no error here in fact. The average value comes out to be 0.5, yeah. So, the average value, the average power is going to be 0.5, which is consistent with the in this case I have taken phi is equal to 45, and what you realize here is the average value in fact is going to be less than 0.5. So, although the current and voltage are exactly the same as far as the magnitudes are concerned, there is now a phase shift between the current and voltage, and since the current leads the voltage, phi is actually the angle of lag. So, it lags the voltage, then you will find that in fact for some time in the cycle, in fact instantaneous power is also negative. So, such a circuit will not always draw power. At some parts of the cycle is actually giving back power giving power back to the source. So, that is a very interesting point which happens in circuits in which the current and voltage are not in phase. There is some exchange of power from the source and the load. Exchange, I mean there could be in fact some power taken back from the load in some part of the cycle. But if you notice, it is not very easy to infer from this diagram that if you take the average value of the red, which is the instantaneous power, a red waveform, which is actually oscillating at twice the frequency of the voltage and current, you will find that the average is above 0. So, you are having a situation where current average is above 0, but instantaneous value at some parts of the cycle are in fact negative. And if you make the phase shift, phase lag 90 degrees, a very interesting thing happens is that you have got a 0 average power. So, for half a cycle power is going back to the a quarter of a cycle, you see power is going back, then it is back, it reverses sign, then it is again pushing back power and again absorbing power. So, you know this happens, it absorbs twice power from the source during in a cycle, and twice in a cycle it actually there are contiguous period in which it gives back power to the source. So, there is a constant exchange of power, and but the average value here is 0. So, actually for example, if you connect a inductor across a voltage source or a current source, sinusoidal current source across a capacitor, you will find in fact that the voltage and current have this 90 degree relationship. If a pure capacitor and inductor, this is the ideal one, and if you assume the natural transient dies down, you come to steady state, you will find that in fact there is a 90 degree relationship. What does this mean? That the average power is 0, the capacitor and the inductor as elements, the ideal capacitor and inductor do not dissipate any power, they only take for some time some power from the source and return it back. But the important thing to be noted here is, in this case as in the previous cases, the current is still the same, the magnitude of the current. So, what it means is that you have these elements which are not dissipating any real power, but still nonetheless drawing power from the source. So, that is a very interesting thing, that in AC circuits you may have to live with such components which draw current from the source, but do not dissipate any power on the average. Okay. So, that is an important point in steady state, again please remember. Yeah, so you can actually do the same analysis with minus 45, and since remember that the average power depends on cos phi. So, minus 45 and plus 45 have the same amount of average power, but the point in the cycle where the power reverses direction has changed. So, for phi is equal to 45, as you shall see once, can you just go back? Yeah, and with phi is equal to, so at different points in the waveform you will find that it goes negative. Yeah, different points in the waveform we are finding it is going negative, but otherwise the average value is the same. So, in fact, if you use the formula sin phi, Vm Im sin phi, you will find that in this case you have got the reactive power absorbed from the source is in fact Vm Im, half of Vm Im sin of minus 45, whereas in the earlier case it was Vm Im by 2 sin of plus 45. So, there is a reversal. So, the reactive power in some ways captures whether phi is plus 45 or minus 45. So, that it is sign kind of sign sensitive, whereas if you look at the real power, it is cos of phi. So, it's if you multiply phi by minus phi also, the average value does not change, average value of the instantaneous power. So, remember, so what it means of course is that if you have got so reactive power, one thing you can be assured of is that the instantaneous power is going negative at some parts in the cycle. So, so if you have got reactive power, it also, another thing we can infer is that power is although the you are giving power back and forth, for some part of the cycle you are in fact giving power back to the source. Okay. Now, what implication does it have? As I mentioned some time back, in all these cases I have kept the current as equal, I mean 1 ampere, the peak value, but the average power really depends on the phase shift between the current and the voltage. Okay. And so, you may be drawing the same amount of current, but you may not be dissipating the same amount of power. When phi is equal to 0, it is like having a resistive load, and you see that instantaneous power is always positive, although it is still varying at twice the frequency. So, that is the an interesting point which you should remember. Yes. So, reactive power being 0 would mean that instantaneous power is not going negative for any part of the cycle, whereas in this case the average power is 0, and power is in fact in this case reactive power is dominant in some ways, and while there is no active power. Yes. So, just to summarize, single phase instantaneous power is always oscillatory. If phi is equal to 0, the instantaneous power is always positive. In fact, it works like this for a resistive circuit, even if it is not exactly a resistance. For example, you can have a RLC circuit in which omega L is equal to 1 upon omega C. Even in that case, the series resonance case, the circuit behaves like a resistor, because the imaginary components, that is j omega L and 1 upon j omega C, cancel each other. So, it behaves like a resistive circuit. So, in this case, if you got a pure resistance or a circuit which appears like a resistance to the source, you will find that Q is equal to 0, although the instantaneous power is oscillating, it is always positive. If plus or minus 90, then only a 0 average oscillatory component is present. This happens when you have got circuits equivalent to inductors and capacitors. I say equivalent to inductors and capacitors because we shall see later that you can in fact have circuits in which you can make you have got an active source in the low, I mean what you have connected to your main source, that is V, what we have called here, is connected to a kind of box which behaves like an inductor and capacitor. Even in such situations you can have plus or minus 90, and in that case P is equal to 0. P is called the average power, real power or active power. Q is defined as the reactive power. So, irrespective of when you talk of the meaning of Q, if your Q is non-zero, you can infer that in fact there is some power being exchanged from the source, going back and forth from the source, and in fact you can have a non-zero value of P and a non-zero value of Q as well. But remember that Q is also sensitive to the sign of phi, so it can in fact tell you whether you are lagging or leading, because sin phi changes sign depending on phi. So, if you are in between phi is equal to 0 and phi is equal to plus or minus 90, in that case you will have both P and Q to be non-zero. So, any circuit which is drawing reactive power can be said to be drawing more current than what is necessary to dissipate just the average power. Okay. So, because there is unnecessary back and forth of power taking place. Also, one more interesting thing is we can define tan phi to be Q by P. In fact, not define, it turns out that tan phi, which is in fact the phase lag of the current with respect to the voltage, is simply Q by P. And another thing is that Vrms into Irms, which is also half Em Im, is also equal to root of P square plus Q square. So, this is just something which we see directly. So, what it means of course is that Vm Im by 2 or Vrms into Irms is always greater than or equal to P or Q. This is called the apparent power. Remember that S is dependent only on the magnitudes of the voltage and the current. So, in some sense S, when you design an equipment, what is often very important is in fact this S, because voltage in fact when you are designing especially a high power equipment, the voltage will determine how you have designed your insulation, and the current will determine how thick conductors you use. So, the product of these two in some sense gives you an idea of the size of the equipment and the kind of currents and voltages it will be handling. So, S, which is an apparent power, is in fact turns out to be root of P square plus Q square, because we have defined Q in a certain manner. Pay attention to what I said some time back, that if you have got a circuit which draws reactive power, remember all these concepts make a lot of sense only if for sinusoidal steady state circuits with linear components. So, please remember that somewhere in the back of your mind. Remember I mentioned that if you have got non-zero reactive power, you are drawing more current than what is necessary to dissipate the amount of average power that you are dissipating. So, you are drawing more current than what is necessary to dissipate a certain amount of average power. What it means is that if Q were to be 0, then you would draw lesser current, okay, for the same amount of dissipated power. So, remember these important things. So, in case you are drawing more current, so if you have got a circuit which has got real and reactive power both non-zero, what you will notice is that you have to design your supply system for both P and Q, because what happens is the current is determined both by P and Q. So, even if your example you have got a circuit which dissipates an average power of 60 watt, but it also draws some reactive power, then you will have to design your supply system to supply a current such that both P and Q are catered to. So, this is an important thing which you should remember. The units of real power is in fact megawatt or watt or kilowatt, it is watt in MKS units. The units for Q have the same dimensions as those for P, but we typically use we call the units as volt ampere reactive. So, VA with a small r is what most people use as the unit for Q. The unit for apparent power is simply volt ampere. All the three units have the same dimension, but it is implicit that when somebody says the volt ampere is 100 MVA, then it means that the apparent power handling capability of that equipment is 100 MVA. Whereas, if real power, for example, a turbine of a generator may be rated at 210 megawatt. So, what it means that the real power it can actually give is 210 megawatt. Okay. One or two interesting things which you should remember is that KVL and KCL applies to phasor quantities. So, when you are talking of sinusoidal steady state, you can very easily show that in steady state, since the current sum of currents at a node are equal to 0, it also means that if all of them are sinusoids of the same frequency, it also means that the phasors, corresponding phasors, sum of all the current phasors incident at a node also are 0. And as a result of which S, which if you look at what I have shown you before, S is equal to, if you look at the previous slide, root of P square plus Q square, and Q by P can be considered as tan phi, then actually S can be actually also represented as a complex number. So, I have put it in bold here, the S without the bold is the magnitude of S. So, the bold S is equal can be represented as P plus JQ, it has got both a magnitude and an angle, and that it turns out to be equal to, very interestingly, simply turns out to be equal to V multiplied by I star, and this multiplication sign, this is not a curl, remember, it is not a cross product, it is a simple multiplication of two complex numbers. Okay. So, in fact, you can easily correlate our phasor analysis to the instantaneous analysis, because S it turns out comes out to be equal to Vs into I star, star is the conjugate of the phasor. Okay. So, you will find that if Vs is like 100 angle 0 and Is is what we got 5 angle 58, like can we go to that circuit which we write in the beginning. So, for example, these of course on RMS values, I have shown the phasor convention here uses RMS values and not the peak values. you will find that in this case, since I am using RMS values, the power will come out to be, S will come out to be V I star here, okay, where V is defined by the Phasor convention of a Phasor convention to represent the sinusoidal function there, and I is also using phasor, the RMS value. So, these two phasors, if you take the multiplication of them, that is V into I conjugate. So, it will be the I conjugate means you have to multiply this by minus, a minus sign, and then take the product, and it turns out that this is equal to the average power plus J into the reactive power as defined before. So, that is a very interesting thing. So, actually if you look at the left hand side of this figure, if you take V, the instantaneous value and multiplied by the instantaneous current value, the two components of the instantaneous power will actually come out to be, can be easily obtained by simply multiplying Vs into I star. The real part of that will, in fact, the real part of V I star will come out to be the average value of P, which is equal to V into I, the instantaneous values. Okay. So, that is very interesting. So, you can actually stay in the phasor domain, you do not have to come back, in case you want, you need not come back to the instantaneous values, you can do most of your computational work simply in the phasors, with the implicit, of course, that the phasors represent sinusoidal quantities in the time domain. Yeah. So, if you go further, you will, as I mentioned, sometimes S is greater than P when reactive elements are present, implies more current is drawn for the same amount of P, a fact which I mentioned some time ago. This of course results in more losses, more voltage drops in case we talk of transmission lines. We have not yet actually discussed transmission lines in detail, but you can look at it as if there is a source with a source impedance, and there will be voltage drops across the impedance if you draw more current. Okay. Bigger equipment, because why bigger equipment? Because it has to draw more current than necessary to dissipate the same amount of power for the same power rating, average power rating. P, remember, is the average power. It has got a very specific and easily understood meaning, that is, it is the average of the instantaneous power over a cycle. We use the convention, of course, we define Q as half of Vm Im or Vrms into Irms into sin phi, and phi was in fact the angle of lag with respect to the voltage, and the current was being drawn from the source. So, in fact, the kind of situation we considered, Q is positive in such a situation, means that you are absorbing positive reactive power, whereas as a capacitor in fact absorbs negative real reactive power because phi is minus 90. So, this is the convention which is used. Remember, the current direction is into the circuit from the source. Reactive power is defined as Vrms into Irms into sin phi, where phi is the angle of lag with respect to the voltage. So, what we actually see is that an inductive circuit absorbs positive reactive power, where a capacitor absorbs negative reactive power. So, this is the kind of convention we will use. So, remember, source is assumed to be voltage rise, V source, this is I, and this is your circuit, and in this case we use Q is equal to V RMS I RMS sin phi, and phi is the angle of lag of this current with respect to the voltage. Under these circumstances, what I have mentioned is true. That is, if you have got an inductor or an inductive circuit like a RL circuit, you will find that the current lags the voltage. Because it lags the voltage, you will find Q comes out to be positive. We say that the Q is being absorbed because the direction of current is this way. We say that the inductor absorbs positive reactive power. Yeah. So, what are the different, if you look at different elements in a power system, you will find that synchronous generators, we will understand these things a bit later. Synchronous generators are some active sources can generate or absorb reactive power. Overhead lines can absorb or supply reactive power. This is not surprising because a transmission line has both distributed capacitive and inductive parasitic elements. You can call it parasitic, but if a transmission line is long, these are quite dominant effects. You can no longer dismiss them as parasitic, but the fact remains that they can absorb and supply reactive power. Cables, normally the kind of cables we encounter in power systems of lengths, a few tens of kilometers, they generally generate reactive power. Of course, the question is, can a cable also absorb reactive power? The answer is yes, it can. In theory it can, but for most practical situations the capacitance of the cables is quite high, and for most realistic lengths of cables you will find in fact that they generate reactive power, especially at 50 hertz. Okay. So, this is not universally true for all cables in all situations. I am talking of cables used for electrical power supply systems. Why this is so is something we will learn a bit later in this course. Then transformers, they generally absorb reactive power, because they are basically mutually coupled inductive circuits at the frequency ranges of our interest. Electrical supply systems are around 50 hertz. Loads are normally absorb reactive power, but that is not universally true. So, I use the word normally. Compensating devices are devices like capacitors and inductors which you connect to the supply system so as to compensate for any absorption of supply by the load. So, these are called compensating devices. Yes. In fact, you will find that this this table which is taken from Kundur's book, Prabha Kundur's book on power system stability. In fact, you just look at the second column of this and the first column of it. It tells you the power factor. In fact, the P divided by S is equal to cos phi, and cos phi is also called a power factor. So, cos phi of a load, if it is 1, it means it is behaving mostly like a resistive load. So, if you look at these various loads here, the power factor which is cos phi in fact is 0.9 or between 0.8 and 0.9 for air conditioners, water heaters, ovens and fryers, deep fryers. In fact, these are all 1 because they are essentially heating elements, they are resistors. So, all your geysers and boilers etc. are usually heating elements, whereas things which use motors etc. in fact, you may find that they are having a power factor which is less than 1. Incandescent lights of course again have simple heating elements, and therefore, they have a power factor of 1. There are some other characteristics, but these we shall learn a bit later. Just concentrate right now on the first 2 columns. So, power factor, remember, is cos phi of the load. Okay. So, if you connect this load to the supply, it may in fact have a phase shift between current and voltage, and that cos of that phase shift is in fact what you see here. But remember, one important point is that this is not definitive. In fact, you can have designs in which you can have variations in this. This is just simply to give you an idea. Okay. Yeah. So, I mentioned some time back that you may wish to connect compensating devices. Here I have shown compensating capacitors, which may actually cancel any. For example, if you got a load which is inductive, which is drawing reactive power, in fact, you can compensate for that by connecting devices in which the current leads the voltage. And in fact, if you got a current which is leading the voltage and current which is lagging the voltage, and you sum them up, you will find in fact that the sum of them is some part of it will cancel, may not be exactly cancel, but may not exactly cancel, but some of it will cancel out, and you can in fact reduce the amount of current being drawn from the source. So, the utility sees a more closer to unity power factor if you use compensating devices. Yes. This is something regarding various loads which is not relevant at this point of time. So, we will in fact discuss these things a bit later. If you look at this, what you pay for, electricity you pay for, this is just a snapshot from one of the articles which came in 2018, giving the proposed and existing tariffs, it will give you an idea. So, we usually use kilowatt hour and not watt as a unit when we define 1 unit of electricity. So, 1 unit of electricity is kilowatt hours, which is in fact the dimensions of energy. So, you are in fact most of us, especially in domestic having domestic appliances or domestic loads, are paying for in fact the energy cost, kilowatt hour, that is power. The average you have to multiply power and time. So, if you have got a constant power, then you simply multiply it by time, that will give you the energy. In case power is varying with time, you have to integrate the power using time as the variable, and that will give you the energy, and we are paying for energy. So, when I get a bill, it is usually the energy bill which I am paying. And just to give you an idea, we have got, for example, if you draw up to 100 units in a month, you have to pay 4 rupees 25 paise per month. This is just to give you an idea of 4 rupees 25 paise for a unit of electricity. Of course, if you are a heavy consumer, the electricity board charges you more. So, this is right now the tariff chart, which is this is giving you rather an idea of the kind of tariffs we have for energy in our system. These things change, so it is not, you should not take these numbers as final, but you get an idea of depending on how many units you consume, the electricity board actually gives several slabs and charges you for the energy consumed. Okay. So, if you look at typical loads and the energy, it is given in the previous slide. Yeah. So, this is something you can just look at, and what you notice in fact appliances, especially domestic appliances which are given here, the things which consume a lot of power are in fact air conditioners and geysers or boilers. So, all these and room heaters, these are all heating elements and they consume enormous amount of energy. Okay. So, this is with this on this note, I will just end my lecture today. In the next session, we will start going more towards electricity supply systems, especially 3-phase systems, the kind of connections we have, and some other interesting nuggets about the electricity supply system.